Okay, so let's do one example here of a straight wire. We're going to use the integral form. I'm actually going to use the gravity acceleration form, which I can write as negative g integral over the volume, or over, in this case, we're not going to have a volume, over the region of density times r hat divided by r squared d dv, or I don't have a volume, so I will call it dr, dr, capital R. Okay, let me set up the problem. Got my equation. This is just taking this form and then applying the definition of the gravity acceleration to get that integral form for gravity acceleration. So what's the gravity acceleration of a straight wire? And let's see if I can draw this. A little hard to draw these kinds of things in 3 dimensions, but see what we can do here. Okay, what you should be able to see here, and again, it's going to be a little bit hard to see, this is like a 3-dimensional form here. So I've got x, I've got the z-axis, and I've got the y-axis. Okay, so again, it's probably a little hard to see, but hopefully it kind of makes sense. X coordinate axes, y coordinate axes, z coordinate axes. And then what I'm going to do, maybe I'll use a different color, is I'm going to have a wire, a thin wire, infinitely small in thickness, along the z-axis, and that wire is going to be from minus a to plus a along the z-axis. So a is just some number. It's just some length of wire. So don't worry about what a is too much. We're going to end up taking the limit as a goes to infinity here in a minute. But for right now, we have a wire that's along the z-axis. We have our x and y-axis. And then we're going to take the measurement, the gravity measurement, at a point P. Again, we always call our observation point P, at some distance here, some distance from this wire. We're going to have an effect at P. So again, here's our integral. We're integrating. Where do we need to integrate? We need to integrate over all the locations where there is some density. So we're going to end up integrating along the z-axis, this infinitely thin wire, from minus a to plus a. So if I go and start putting in my numbers here, I'll have minus g. That doesn't change. I'll have minus a to plus a. I'm going to integrate just along the z-axis. So then let's see here. Density here, the book uses lambda. It's really just density, but because it's not 3 dimensions, it's only kind of a 1-dimensional density. It's really density per unit length. That's where this lambda comes from. I don't know if it's more confusing to use it or not, but the book uses it, so I will use it as well. So density per unit length, that's our lambda. And then what do we have here? We have r hat over r squared. Now, the thing to notice here is that what is r hat? R hat is going to be our 3-dimensional unit vector. So if we draw an arrow here, so we're looking at a little increment, dz. We're going to integrate. So we're going to have dz over here. We're going to integrate from minus a to plus a, our unit density, times dz, and then we need to have our r terms in there as well. A couple things to note. One thing to note is that there's no gravity in the y direction, the up-down direction here, the vertical axis. Why is that? Because the wire is directly along the z-axis. So there's no pull at point P. There is no pull along that vertical axis. The other thing to note is that at the point P, we exactly cancel out because we're exactly between the endpoints of the wire. So the gravitational pull from this half of the wire is exactly the same. It's going to be pulling in this direction, but then it's exactly canceled out by the wire pulling in this direction. So what that means is that the gravity field for this point P from this wire is going to be exactly along the x-axis. So we only have the x-axis to worry about here when we're looking at the gravity field. So we've got our equation set up here. We need to get our 1 over r term. So I've got 1 over r. Here it's 1 over r squared, but I'm going to use this r hat thing. I'm going to use the fact that this is only going to be in the I hat direction. So remember we had I hat, J hat, K hat for the X, Y, and Z directions. So I'm going to want to call this an I hat. And in order to do that, I'm going to decompose this R hat into a X over R. So this is like X over R. R is the distance here, total distance. And then X is just the distance on the X-axis. And then I have so then R hat is going to be equal to X over R times I hat. So now I can finish off my equations. This is going to become an R, and I'm going to have an X there. Okay. Very good. So now I can do this integral. I'm going to do some trig substitution. It's in the book there. I'm not going to go through all of that. But basically, we're going to do some trig substitution, and we're going to get that this gravity field, so this is the gravity field from a finite line, is going to equal the following. And where am I going to write this? I'll write it here. Make sure I put my vector there. We're going to end up with negative 2g times lambda. Got to make sure I have my unit vector in there because that gravity field is pointing in this direction. Okay, so I've got this integral. I'm doing some trig substitution. You can see the process in the book, and you end up with this gravity acceleration for a wire from minus a to a, infinitely thin wire, along the z-axis for a point P, which is exactly on the x-axis, located at a point X, right? So this X is the location on the x-axis of that point P. Okay, great. So we have some equation, finite wire. Like, how is this useful? This doesn't really seem that useful because wires are not infinitely thin, for one thing. And yes, we have a finite wire, but it's not clear how this would become useful. How it becomes useful is because what we're going to do is we're going to first take the limit of this as a goes to infinity. In other words, instead of a finite wire, we'll have an infinite wire. And then an infinite wire, it turns out, can be used as an approximation for a 2D density distribution. So in 2D, if we took the xy plane as a slice, z is in the perpendicular to that plane, we can basically assume that a wire of infinite length is like a 2D point mass. So 2D point mass is, in 3D, a wire of infinite length. Those go back and forth. And then what we're going to end up doing is we can integrate the solution for this wire over some two-dimensional distribution. We can get a generic 2D distribution of mass using this wire solution. So let's go ahead and take the limit here. And again, I'm kind of running out of space, but it should be very easy to see. This is square root of x squared plus a squared. Okay, x squared is small, it's right here. But as a is going to infinity, the a term is going to be the most important, right? You can see here the x is going to be much smaller than a if a is going to infinity. We have square root of x squared plus a squared. So a is much bigger. That's approximately square root of a squared. Square root of a squared is just a. Then we have a over a, the a's drop out. So all of that in mental mathematics to get down to this very simple solution. Just simply 1 over x times I hat. And so there's no other coordinates in here. It actually doesn't matter where you are in the xy plane. This is going to be, or I should say in the xz plane, I guess, along the x line. It doesn't matter where you are in this xz plane along the x line. It doesn't matter if you're over here or over there. As long as the line is infinite, what only matters is the distance on the x direction to that wire. So in 2 dimensions, this should kind of make sense, right? In 2 dimensions, it's just the distance to that wire that matters. So there's no y or z component here in this solution. How does this compare, by the way, to our 3D model? In 2 dimensions, we don't have gravity field is g times mass divided by r squared times r hat. We have 2 times g, so we've got a factor of 2 in here we did not have before, and now we have just 1 over x. 1 over x. So our 1 over r squared term has become a 1 over x term, and that's because we're specifically in the 2-dimensional limit. Okay, so good. That's our gravity potential at a point basically in 2D space, but for a potential of an infinite wire. Now, I'm sorry. the gravity field from an infinite wire. Now, I haven't talked about potential yet. So you can imagine as you take this wire to infinite length, what's the total mass from that wire going to become? It's going to become infinite mass, right? So infinitely long wire will have an infinite mass. And that means if we just take our potential here and we integrate that mass, we integrate something that's going to infinity, our potential is going to become infinity. Okay, well, that's not very useful. And it's because of this approximation. So basically, we're turning something which should be 3D into a 2D problem by adding an infinite mass. Okay, hopefully you see that how that works. In reality, we would never have an infinite mass because we do not have infinitely long wires or anything else, right? There's no infinite physical quantities. So what we have instead is we've approximated this to get to a 2D distribution, or we're using an infinite wire as an approximation of a 2D distribution. And now that has this odd thing that we now have infinite mass, which gives us to infinite potential. So what we can do is the following. Here's our density or mass distribution, dm, right? We also said this was equal to g times the integral of rho over r dv. So here is our potential, right? Potential. So now in 2 dimensions, we're going to have potential is equal to, and this is our for our thin infinite wire now. So we'll have gravity constant. We're going to use our lambda again. So again, that's our unit density per unit length of our wire, our thin wire.
Right.
We have 1 over r and dz. So we're going to take our finite, we're going to start out with the finite length wire. We're going to take the limit as a goes to infinity. For the potential, we're going to get some complicated expression, which is a function of a. So we're going to get g times lambda times something which is the log of a function of a. I'll just call it f of a. This is the key thing in 2 dimensions. In 2 dimensions, we get logarithms. Logarithmic potentials are what comes out of having these infinite length wires, infinite distributions that we use as approximations for 2D distributions. Okay, so you get these logarithm terms. There's some function of a. That function of a is going to become infinity. It's going to get too large. And that's because of what we mentioned here. If we take the limits as a goes to infinity, we'll end up with an infinite mass that would lead to an infinite potential. The book shows us a mathematical trick that we can do. And basically, the key thing is that we're going to normalize all the distances in this 2D world. So again, we're working towards getting to a 2D distribution. We're going to normalize all the distances to be between 0 and 1. And if we do that, then everything's well behaved. And so the key thing for you to understand from what the book says, and this is section 3.3.1 in the book, the key thing to understand is we're just going to assume everything has to be less than 1. All distances have to be less than 1. If the distances are greater than 1, we're going to normalize them in some way so that they become less than 1. Okay, and then you are able to then simplify down the mathematics and you get something where this now becomes essentially 1 over r. So we end up with, and then I have a factor of 2 there. So 2g lambda, we still have our factor of 2 from the case over here, right? G, capital gravitational constant, lambda, and then instead of being 1 over x, we now have log of 1 over x. So this is the gravity field. This is the gravity potential, right? The gravity potential for a 2D distribution or for an infinitely long, thin wire. The key thing, like I was telling you, is we're not really interested in the distribution of thin wires, infinitely thin wires that are infinitely long. What we're going to do is we can use those now as approximations for the gravity field of 2D, arbitrary 2D distributions, arbitrary 2D shapes. So now let's say that I just have a 2D axis, x and y, and maybe I have some arbitrarily shaped mass. And I say this mass has some unit density lambda, and I want to know in this 2D world what's the gravitational potential of this thing? How could I do that? How could I calculate what the potential or field How could I calculate what the potential or field would be from this 2D distribution of mass? Hopefully, you're already thinking of the idea. It would simply be the integral, and in this case, a double integral, over the area of this thing of our distributions, of our potentials or the fields, depending on which one we are looking at. So we can calculate what the gravity distribution in 2 dimensions would be from some arbitrary. We could do a cylinder. We would just take, in that case, if we had a perfect cylinder, let me draw that. See how well I can draw a perfect cylinder. What's the radius of a circle? Well, the radius of a circle is just pi r squared. So now we could take the gravity field. So the gravity field for a perfect cylinder is just simply going to be 2 times pi r squared. R here would be the radius, so let me call that a. So this has a radius of a, pi a squared. So 2 times pi a squared times gravity constant times density times 1 over r. In this case, it's right back to 1 over r because now we're in 2 dimensions instead of just 1 dimension. And then r hat. So that's equation 3.20 in the book on page 57 of the Blakely textbook. So we can calculate now arbitrary gravity potentials for arbitrary distributions. And there's an example on the next page in the book where they have some strange shaped thing, and they're just integrating that over that surface. So we're integrating the potential for a thin infinite wire over the surface of some distribution, and we can get the distribution of that, or the gravity potential and the gravity field for that shape. So hopefully now you're catching on to the idea here. Gravity is really nice. Principle of superposition. Things add up together. The gravity field from 2 points is the same as the sum of the gravity field from each individual point by itself. And so we're going to make use of that. We're going to make use of that in 3 dimensions by imagining little boxes, each of which have constant density, and we're going to add up the mass of all those boxes to get the total gravity potential for that mass distribution. We might integrate. If we have a continuous density distribution, we would integrate over that volume. We have now approximated what a point source looks like in 2 dimensions, and we can integrate that point source in 2 dimensions over some area to get the gravity potential in 2 dimensions for that mass distribution. And we had to do some mathematical tricks to get there, but doing those mathematical tricks, it's fine. In 2 dimensions, we normalize all the distances, and we're okay to do that. Obviously, in the real world, we want to work with 3 dimensions. And in that case, we don't have to worry about the mathematical tricks or anything like that because the potential is well behaved in 3 dimensions, which is where we live anyway. All right, so that's a lot about gravity potential, principle of superposition, distribution of different distributions of masses. With that, I'll see you in the next video.